Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. Welcome back. Today's lesson is all going to be about solubility. So solubility is the ability to dissolve, and what we need to understand is everything will dissolve in water at least a little bit, but we have to set some parameters, and we got to discuss how we communicate solubility. So for instance, solubility is actually measured in grams per 100 milliliters of a solvent. However, it could also be done in grams per 100 grams of water. Now, 1 gram of water is equivalent to 1 milliliter of water at standard conditions, so 1 atmosphere of pressure, 25 degrees Celsius, etc. So that's one definition. The second definition, which is probably more appropriate, is molar solubility. So the majority of the time, when we look at how much something dissolves, we look at the number of moles that will dissolve in 1 liter of solvent. And again, the majority of the time here, we're looking just at water as being the solvent, not really anything else. So this is measured in moles per liter. And when we start doing calculations, we're going to be doing lots of calculations in moles per liter. So the example substance I picked out was salt. So for instance, you can dissolve 36 grams of salt in 100 milliliters of water, which is a lot. I mean, that is a lot of solid that's dissolving in there. But we know that sodium chloride is a very soluble compound. Sodium is a group 1 metal ion, and group 1 metal ions have extremely high solubility in water. Now, if I was to convert that 36 grams per 100 milliliters into moles per liter, that would be the same as 5.41 moles in every liter. Now, I'm just going to quickly discuss something now. We'll return to it, which is, well, what if I added more than 36 grams to 100 grams of water or 100 milliliters of water? And the simple answer is only 36 would dissolve. Whatever extra I put in, let's say I put another 4 in there to make it 40, those 4 grams would stay at the bottom of the beaker and they would remain solid. I'd be past its saturation point. Now, if I was under 36 grams, it would still dissolve. There would be no solid there. I'm just under my saturation point. Same concept here. If I was to add 5.5 moles of salt in 1 liter of water, there would be a little bit of solid at the bottom. Anything under 5.41, there would be no solid left at the bottom of the beaker. So those are our definitions. Molar solubility is probably the more important of the two. It's the amount of solute which dissolves in 1 liter of solvent. Now, you do come across solubility a little bit. Solubility charts are very common. We're going to look at one today. It really likes to look at how many grams dissolves in 100 grams of water. Before we move on to that though, let's do a quick recap of how we use the solubility table found in your data book. Now this is a solubility for common ionic compounds. What you will notice, there is no molecules in here. We don't have NH3, not NH4+. NH4+ is an ion. We don't have alcohols, we don't have sugars. Molecular compounds, you have to look up their polarity, and you have to figure out, are they polar enough to dissolve in water, which we touched upon in our previous lesson. This table is strictly for ionic compounds. Okay, so this is the way that all solubility tables work. They have to have some parameters of what they consider to be soluble. That's why if you're, say, using different solubility tables from different references, you will have different guidelines. So if you look at the bottom of this table, it says, note, this solubility table is only a guideline that is established using KSP values. This is an equilibrium value. You guys don't know anything about that yet. But the parameter is this. A concentration of 0.1 moles has to dissolve in 1 liter to be considered soluble. This is roughly 10 to 30 grams per liter, depending on the molar mass of the substance. So I'm going to point that out over here. This row essentially means this thing is quite soluble. If you fall in this row, it essentially means that you're not very soluble. So this is the baseline. The solubility has to be greater than or equal to 0.1 moles of that substance, has to dissolve in 1 liter of water. If this is true, then that solution is considered to be aqueous and highly soluble. The one below says, yes, it does dissolve, but it dissolves less than 0.1 moles per liter. So for instance, some of these might actually be really soluble, like maybe Mg2F might have a solubility of 0.009 moles per liter, which is really close to 0.1, but you have to have a cutoff at some point. I always like using sports analogies. And so, lots of people play hockey, but there's only so many professional hockey players. So professional hockey players are super soluble. And then other hockey players that aren't professional but can still play fall in here. So I know for a fact in my classroom, I have a solubility table, and some of these insoluble things come as soluble on that table, and they're insoluble on this table. So for instance, hydroxide, strontium is actually quite soluble with hydroxide, but it doesn't quite make this. It's just a little bit off. But if you look at, say, an AP data book, and you look at what they consider as being soluble with hydroxide, hydroxide would be considered soluble. Anyways, let's give a question a try. So let's say we had a number of ionic compounds, like down here at the bottom of the page, and you were asked, determine if these are soluble or insoluble using the data chart above, okay? So for the most part, students would look here first, and often you're looking for the anion in the compound. So for instance, down here I have NH4 plus or OH minus as part of this compound. So I split it into its 2 ions, and then I have the option of looking for NH4 plus or OH minus along the top. Now my natural instinct would be to look for OH minus because almost everything in here is a negative charge. So I'm mostly focusing on things that are anions. So this is what I do. I go to the end of my chart, I find hydroxide, okay, that's good. I check to see if NH4 plus falls in this first group, okay? So it says OH minus is soluble with group 1 ions, which would include potassium, lithium, sodium, all of those. And it is also soluble with NH4 plus. Well, over here it is attached to NH4 plus, which means it falls in this group, and that would make it quite aqueous. Now let me pick a different one here that might not be so soluble. Having a look at number 5, maybe I'll do this one. So I got 2 ions in this compound. I got copper 1 and I've got bromide. Now I understand that this is copper 1 because bromide has a 1 negative charge, and there's 1 of each, which means their charge balances. This must be copper 1. I go to the top of my solubility table. I check for copper plus or bromide. I'm really focusing on bromide because this is all negatives almost. Here's my bromide. I go down. It's soluble with almost everything, so they just say most. They can't list everything. I continue to look down. Oh, look, there's copper 1. So if it falls in this row, which it has, here's copper 1. That is insoluble, and I would say it's solid. Now, to be crystal clear, some copper 1 bromide is going to dissolve in water. It's just not going to make this amount. 0.1 moles will not dissolve in 1 liter of water. That's the cutoff of what is soluble and what is not soluble. So what I'd like you to do now is I would like you to solve for the rest of these problems down here. So hit pause, and when you're done, come back and we'll go through the answers. Okay, now that you've had a chance to work through these, let's go through them. First one, I'm looking for NO3 minus. I see I have NO3 minus here, and it's soluble with almost everything. I do not see KNO3 down here, which means it is soluble. The other way I could go about it is group 1 metal cations are soluble basically with everything, and potassium is a group 1 metal ion, so it is soluble, so this is aqueous. Next one. I have CH3CO. I look up here, CH3COO. All right, it is soluble with almost everything. We just got to double check that it's not insoluble with something down here. Oh, there is this very specific one. It is insoluble with silver. What you'll notice about this square here is it looks a lot different than the rest because these things are so soluble with everything that there's only 4 specific exceptions. So rubidium perchlorate, cesium perchlorate, silver acetate, mercury acetate. Those are the only exceptions which are insoluble based on 0.1 moles per liter. So this is solid. Next one, I've got chloride. So I'm going to go look for chloride. Here's chloride. I go down, it's insoluble with copper, silver, mercury, lead, and TL. Calcium is not one of those things, so it must fall under most, and therefore calcium chloride is aqueous. We also know it's aqueous because that's in a hot pack, which releases energy, and we know it does that when it dissolves. Okay, number 6. A lot of times people find this one tricky. So I've got sodium ion, and I got sulfide ion. And so my immediate response is always to look for sulfide because it's a negative charge. And when I go across here, I don't find sulfide. So then I got to look for sodium. Well, sodium would fall under group 1 ions, and therefore this would be quite soluble, and I would call it aqueous. Whenever I see a group 1 metal ion like sodium, potassium, lithium, I immediately know that it's soluble. I usually don't even check this chart. I just understand group 1 metal ions with pretty much everything is going to be aqueous. All right, let's look for our next one. We got hydroxide ion. I go across the top. Here's hydroxide. It's attached to magnesium. Now, magnesium is a group 2 metal ion, so it doesn't fall under group 1. It's not NH4+. That means that my Mg falls under most. So this was going to be insoluble. All right, our next one. This is sulfate, SO4 2-. Now that must mean that this is copper 1 because it's got a subscript of 2. I need 2 of these to balance out the 2 charge over here. So I'm going to go to sulfate. Sulfate is right here. It's soluble with almost everything. I keep going down. Is it attached to calcium? Nope. Strontium? Nope. Barium? Nope. And so on. Nope, nope, nope. That means copper 1 falls under most, and therefore this is going to be aqueous. The next thing we're going to look at is different types of saturation levels. So looking at the terms saturated, unsaturated, supersaturated, and what does this mean, and how do I show this in terms of a chemical equation? So I'm going to stick with this example that 5.41 moles of sodium chloride could dissolve in 1 liter of water. And we're going to start with the easiest definition. If y'all had an unsaturated solution of sodium chloride, I'm underneath the saturation amount of that solute. So we'll make up an example. Let's say we have 1 liter here, and I had 2.5 moles per liter of NaCl, or 2.5 moles dissolved. So I would add that salt in, and it would just look clear and colorless. I wouldn't see any solid in here. It would just look like water to me. It would be a homogeneous mixture. If I had a cup of salt water right beside a cup of Normal water, if it's been sitting there for a while, I can't tell the difference. It looks the same. Okay, so unsaturated means we have to be under that 5.41 moles per liter value. There is no solid at the bottom of the beaker. And we could use a dissociation equation to express that there is no solid. So I could say I got NaCl solid. This has become Na plus aqueous plus Cl minus aqueous. It's all balanced 1 to 1 to 1. The fact that I have a single arrow forward means that all of this solid has turned into ions, sodium ions and chloride ions. I think most people know what unsaturated means, but I hope that cleared it up if you didn't know. All right, the next term we're going to look at is saturated. Now, if something is saturated, you have the maximum amount of solute has dissolved. No more solute will dissolve. And there is usually undissolved solid at the bottom of the beaker. And the solution is said to be in dynamic equilibrium with the solid. So I'm going to explain what dynamic equilibrium means, and I'm going to stick with our salt here. So let's say we had 1.0 liters again of water, but this time I've added 6.0 moles of salt. Okay, so I dump that in. What will happen is our 5.41 moles of NaCl will be aqueous. It will be floating around. But what about that additional 0.59, which would make up the 6 moles? What's going to happen to it? The 0.59 moles, 0.59 moles of NaCl will sit at the bottom as being solid. Now, there's sodium and chloride ions bouncing around this beaker. And what dynamic equilibrium means is this. These things will bump into each other. So I'm going to just call this here a sodium ion. And when it hits the crystal at the bottom, because this sodium ion is just bouncing around this beaker, sometimes it will collide with that solid, and in doing so, it will re-solidify. So it'll become part of the solid. But what will happen is a different sodium ion is going to get kicked out of that solid. So it's called dynamic equilibrium because they are not static, they're dynamic. Particles are hitting the crystal, they're crystallizing, and when one comes in, one has to go out. And I know I'm using lots of sports analogies here, but it's just like if you're changing players in soccer or hockey, if one player goes to the bench, one player on the bench has to come out. It's a one-for-one exchange. So to express dynamic equilibrium, we have to use what we call an equilibrium arrow. So we understand that sodium chloride solid is turning into sodium ions, and it is turning into chloride ions. But when these sodium ions and chloride ions hit that crystal, they will re-solidify, but they'll cause another ion to come out into solution. So how I show that is, this is also going back this direction. Sodium ions and chloride ions are becoming solid at the same rate as the solid is becoming sodium ions and chloride ions. If I'm making this pair, then I'm going this way, and then this has to break down into that pair. So it's dynamic. 2 players go off the ice, 2 players go on the ice. I hope that makes sense. So we use this arrow here if we have a saturated solution because we have solid present and we have ions present. the solid is dissolving, but it's dissolving at the same rate as the ions are coming back together. And in doing so, it creates this dynamic equilibrium. Dynamic just doesn't mean static. This ion isn't static. It's hitting, then it's kicking out another ion. So that's a saturated solution. Something I could do to get all 6 moles of this to dissolve in this beaker is I could increase the temperature of the solution. Most ionic compounds will increase in solubility with an increase in temperature. There actually are some ionic compounds that do the opposite of that, but it's quite rare. I am going to talk about it later in this lesson. So if I was to heat this solution up, salt will dissolve better at higher temperatures, not by much to be clear actually, but it will. And I could get more of this solid to become part of the solution. At some point, I probably could get all 6 moles to dissolve in the 1 liter if I warmed it up. Now keep this in mind. If I let it cool back down to 25 degrees Celsius, which this is based on, you will actually start to see cloudiness. You will see salt crystals forming in the solution, and it'll settle out until it gets back to this 5.41 moles per liter. The last definition of saturation is supersaturation. Now, not all ionic compounds can do this. There's only a handful, I believe. One that does supersaturation really, really well is acetate ion. So something called sodium acetate is used a lot when you want to make a supersaturated solution. So I'm going to build off the concept I just talked about up there. Okay, so let's say I'm just making up a number. 10 moles per liter of sodium acetate would be its solubility, completely making that up off the top of my head. So if I had, let's say, 15 moles per liter, and I had some solid in the bottom here, so I had some solid because only 10 moles per liter dissolves, and I heated it up, it would all dissolve into the solution. Now normally, after you cool it down, what would happen is precipitate would start to come out until you got back to its 10 moles per liter, let's say. Sodium acetate doesn't do that. It actually stays in solution. So I can oversaturate it, even though at 25 degrees Celsius, I'm just, again, making up a number, say at 25 degrees Celsius, 10 moles will dissolve in 1 liter. I could heat it up, dissolve more solid into it, allow it to cool, and the solid will not come out of the solution. It's really cool. If you go to this website, well, it's on YouTube, this is a really good demo of it. You'll be pretty amazed at what it looks like. Supersaturated isn't a big deal for us. I just thought I'd mention it because kids often ask about it, and I always do it as a demonstration. It's really cool. Please visit this site to see what supersaturation looks like and what happens when it gets agitated or a seed crystal is added to it. The next thing we're going to look at is a solubility curve for ionic compounds. So this big graph here shows how much solid of an ionic compound will dissolve at a given temperature. So I'm going to focus in on KCl. It has a nice linear line here. It's probably really easy to work with. But to just give you an idea of how to read this, be the following. At 0 degrees Celsius, I could go up to here, and I know that roughly about 26 grams of KCl will dissolve at 0 degrees Celsius. If I went to, I don't know, 30, I went here, I could go across at 30 degrees Celsius, roughly 35 grams would dissolve, and so on. So if I went to 70 and I went up at 70 degrees Celsius, I would have roughly, I don't know, 47 or 48 grams of KCl that would dissolve in water. There is only one substance in which cooling it down makes it dissolve more. I believe that this is due to its thermodynamic properties. Generally, it's going to be lowering the energy state of the compound in some kind of way. But like 99% of the time, if you increase the temperature of water and you're trying to dissolve an ionic compound, its solubility will increase. On that previous page, we looked at sodium chloride. It's right here. You can see that actually temperature increases barely affect its solubility. But then if you looked at something like potassium nitrate, this has a huge curve going up where it's greatly affected by the change in temperature. So to help you better understand solubility and what happens when you cool a solution, I'm going to pick KCl and we're going to look at it at 4 different temperatures, okay? So let's imagine that we had 50 grams of KCl in all of these beakers. But we're going to give each beaker a temperature and we'll start at the hottest and we'll work our way down. So this is what I'm going to say. This beaker will be at 90 degrees Celsius. And then maybe this one will be at 70 degrees Celsius. And we'll just move down in 20s. This will be 50 degrees Celsius. And this would be 30 degrees Celsius. So what I would do to see if, how much is dissolved or how much can dissolve, I will look at that line for KCl and I'll just do some interpolation on the graph. So for instance, I'm going to go from 90 up and then I'm going to make a line across. So I know it's a rough there, but that's okay. So at 90 degrees Celsius, roughly 52 grams of KCl will be dissolved in solution. So here, this would be then an unsaturated solution because I haven't passed 52 grams. 52 grams is the maximum amount of solute you can dissolve of KCl you can dissolve at 90 degrees Celsius. So this would be unsaturated and it would just look like a pure solution. Now, if I was to do 70 degrees Celsius, I'm going to draw a line up going to the KCl. I'm going to go across and I'm going to say roughly, I know it came at an angle there, I'm going to say roughly 48 grams could be dissolved. So at 70 degrees Celsius, 48 grams of KCl could be dissolved. That means that 2 grams would have to be on the bottom. I'm going to call that 2 grams of solid. This would be saturated. 48 grams would be aqueous. Okay, then I let it cool some more. I let it cool down to 50 degrees Celsius. So I go to 50, I draw a line going up, I go across, and that looks roughly around maybe 42 grams, I'm going to say. So 42 grams of KCl could be dissolved. So I have 42 grams, which is aqueous. They're bouncing around, you can't see them. But now what's left over is 8. So now I've got 8 grams of solid. And again, this would be considered saturated. Last but not least, if it was 30 degrees Celsius, I do a line up, I do a line across, and that looks roughly at about 35 grams. So 35 grams would dissolve. I would have 35 grams, which is aqueous, and then I would have 15 grams of solid at the bottom, making up the total of 50. and I just used one circle for each gram. So 15 grams of solid. So saturated, saturated, saturated. Now going back to supersaturation, if this was sodium acetate, it would be unsaturated at the start, and then as I let it cool down, no solid would come out. It would actually stay in solution even though it's beyond its saturation point. Most compounds, what will happen is the solid will just precipitate out and it would sink to the bottom like this. So this is how you would interpret how much can dissolve based on this chart. So what we're going to do is we're going to answer these 4 questions, okay? Which substance is the least soluble at 25 degrees Celsius? Well, okay, I go to 25 degrees Celsius, which is here. Whichever one I come across and hit there. Okay, this is cesium 3 sulfate, which it touches. So this would be, number 1 would be Ce2SO4 3. So again, I have to go to the temperature which they're asking, 25. Whichever line I hit first, which is cesium sulfate, that's the one that's going to be the least soluble. So which substance is the most soluble at 10 degrees? Okay, well, I'm going to go to 10 degrees. I'm going to make a line going all the way up. I hit sodium nitrate last. That means sodium nitrate is the most soluble at 10 degrees. The solubility of which of the substances is most affected by a change in temperature? What I'm trying to find here is the thing with the greatest change in solubility or the most steep curve that I can find. So if I go back to the chart, there's a couple that are fairly steep, but I kind of noticed this one here. Calcium chloride becomes really vertical the hotter it gets. This slope is very, very steep. Now the potassium nitrate is also very steep, this one here, but I don't think that's curving as vertically upright as the calcium chloride. So I'm going to say the calcium chloride is probably the one that is most affected by the temperature in terms of solubility. Okay, our last one here. At what temperature is the solubility of potassium chloride equal to 34 grams per 100 grams of water? And what other substance has the same solubility of 34 grams per 100 grams of water? Okay, so potassium chloride is the line we were working with. So it was this line. I know it's getting hard to see, potassium chloride. We have roughly 34 grams here at this point. If we go across, that's just under our 35. That would be 34. And I know it's getting quite crowded in here. I'm just going to erase a couple of lines so you can see. And it's the sodium chloride which intersects that point as well. Okay. So it was a 2-part question. At what temperature is its solubility about 34 grams? And that is 30 degrees Celsius. And then what was the other substance? It was sodium chloride. So the next thing we're going to look at is the solubility of gases in solution. So I'm going to start by saying that I have a beaker and this contains soda water. And so all that soda water is H2O liquid and dissolved carbon dioxide, so CO2 aqueous. The carbon dioxide itself, you see it as bubbles. It bounces around the container and hits the walls, and sometimes it sticks. And it also hits the surface of the water as well. Now, if this carbon dioxide particle has enough energy to escape the solution, which means it hits the top and then comes out, you get that fizz along the top, okay? Now, sometimes a gas particle will hit the surface. It doesn't have enough energy, and the surface tension at the edge of the water is so high that it actually gets forced back down. Now, when it comes to gases, kinetic energy always increases with temperature. So as the temperature increases, the more kinetic energy this gas particle has. So let's say this is 25 degrees Celsius, which is fairly warm. That's quite a bit of kinetic energy. Some of these bubbles are going to start coming out. They're going to hit the surface and they're going to come out, and some are going to be redirected back in. But if I then warm up that water to say, or soda water I should say, to 75 degrees Celsius, more CO2 has enough energy to leave the water. So more CO2 has enough energy to leave the water. So now when I got these gas particles in here, they're moving really, really fast. And so when they hit the surface, they're more likely to actually leave the surface like that. So they hit and more of them leave. And so the solubility of the gas will decrease as it gets hotter. The solubility of a colder solution is going to stay fresher. So I'll give you a real life scenario. Pop, if you keep it in your fridge, stays way fresher. And what I mean fresher is it has way more carbonation. When you leave it out on the counter, it's warmer and more of the CO2 will start to move out of the pop, and it'll build in at the top of that space at the top of the 2-liter bottle where there's no solution. The pressure will get higher and higher, and when you open it, you'll hear a louder fizzy pop sound than if you have left it in your fridge. Okay? So as you increase the temperature of a solution, more of the gas will escape. Another scenario which you might be familiar with is increasing water temperatures in the ocean. This changes the amount of oxygen and CO2 in the water, and this actually can really affect aquatic life. Aquatic plants need CO2 to do photosynthesis, and the warmer the water gets, the less CO2 is going to be in there. Okay. Now, in terms of pressure, I'm going to relate this to the bends. If any of you are scuba divers, you'll know about this, okay? So if you increase the pressure on a gas in solution, the solubility increases. Okay, so if I apply pressure from the outside on a solution, this is pressure, more bubbles, more gases can dissolve in the solution. Now, everybody's probably dove at least a little bit in a swimming pool, and you guys know that the further you go down in the swimming pool, the harder the pressure is on your ears because the water is so heavy. Now, when we breathe underwater, we're taking in nitrogen gas at about 80%, and you're taking in oxygen gas at about 20% if you're using compressed gas. Now, nitrogen is an inert gas and it dissolves in our blood just like oxygen gas dissolves in our blood. But under high pressure, we can dissolve much more nitrogen and much more oxygen into our bloodstream. Now, the oxygen, this is used for cellular respiration, which is good. So we have more energy supply because we need sugars and oxygen to do all of our normal functions. The nitrogen is just inert. It's just in there. Now, when you come out of a dive, so when you start coming up, what happens is the gases want to leave. They want to come out of your blood. And when that happens, the gases expand in your blood vessels, and it can cause loss of limb. You can black out. It can cause death. It can cause aneurysms. It can cause all types of stuff. So what divers have to do is they have to ascend quite slowly, ascend, stop, breathe, to allow for the gases in the blood to circulate back to the lungs so that you can breathe them out and they don't get trapped in capillaries and arteries and cause severe bodily damage. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.